Oh my gosh. All right, guys, welcome back to part 2. So let's see what question we're going to be looking at next. So we're going over to number 30, and here's our related rates problem. So a kite 100 feet above the ground moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string have been let out? Okay, so again, we see we're given one rate and we want to find another rate. That's how we know we're in a related rates problem. All right, so what's that process? Well, we read the problem. Now let's draw a picture and use our variables and interpret rates as derivatives. So let's draw a ground, and we're flying a kite. So I'll just do a dot. I won't draw a person. And it says it's 100 feet above the ground. Ooh. Okay. And then after we fly our kite, I'll say our kite's right here, it starts moving horizontally. And it's moving horizontally at a rate of 8 feet per second. All right, well, what variable do we normally use for a horizontal distance? We can call it x, and it's a function of time. And dx dt would be that speed. And it's moving at a speed of 8 feet per second. Moving at a speed of 8 feet per second. And then we want to find, what do we want to find? So it's 100 feet above the ground and it moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string have been let out? Okay, so here is our kite now, right over yonder. And all kites should have a string. And so we're saying, and then this is changing too, right? As the kite flies farther away, you're going to have to let out more string. So we can call this like a z. That's also a function of time. And we are interested in theta, the angle between the string and the ground. And so now we want to find how that angle is decreasing, right? Because as more string lets out, this angle is going to get smaller and smaller and smaller. All right, and we're going to figure it out when 200 feet of string have been let out. And the length of the string is z. Okay, so let's take a look at our picture. So we have, again, we have a right angle. And we have a theta and we have two sides, right? We have a theta and we have two sides. So we have to think what kind of functions or what kind of equations relate angles and sides of a triangle. Well, our trig functions do. Our trig functions do. So we're going to be using a trig function in this case. Let's get theta back into the triangle though. And look at, we have parallel lines, right, cut by this transverse. So we know the opposite angles like that are equal. Okay, so we can get theta back in there. Okay, so now this is our scenario. So we have this right triangle, three variables, x, z, and theta, and then the hundreds remaining constant, which is a good thing, right? We don't want to use a trig function that would incorporate everything like this, like the cosine, because then we don't have any constants. It's just one equation with three unknowns. It's too much. So my strategy is going to incorporate that 100 somehow. So I'm going to choose tangent of theta, and SOHCAHTOA, tangent of theta is opposite over adjacent. So I'm going to write that. I'm going to say that tangent of theta is opposite over adjacent. Okay. There you go. And because we're eventually going to take the derivative of this, instead of writing divided by x, we can also just think of that as x to the negative first. Okay, so now what we're going to do is we're going to take the derivative with respect to time again. because this whole scenario is a function of time. As more time passes, our angle is going to get smaller and the kite's going to get farther and farther away. So we're going to take the derivative with respect to time of both sides, and we're going to use the chain rule. All right, so what's the derivative of tangent, the outside function? Secant squared theta, and now derivative of the inside function. That's our chain rule. All right, and then let's take the derivative of the outside function. So bring down the exponent, subtract 1. And then times the derivative of our inside function. Okay, so we are trying to find d theta dt. And we have that here, right? D theta dt. That's what we're trying to solve for. So if we wanted to solve for d theta dt, we need a couple things. We need to figure out our theta when z is equal to 200, and we also have to figure out our x. Okay, and we know dx dt. Dx dt is given at 8 feet. All right, so let's see what happens when z is 200. So let's draw a triangle down here. I'll do it without all the bells and whistles. We know this is 100. We have to figure out x. We have to figure out theta when z is equal to 200. Okay, and again, we're doing that because that's when we want to find d theta dt, when z is 200. Okay, so what can we do? Well, we can do a couple things. We can use Pythagorean theorem to figure out x. That would be a good place to start. So we know that x squared plus 100 squared is equal to 200 squared. Okay, and we could solve that for x. Okay, so x squared is equal to 30,000. We can take the square root. So square root of 30,000. And I'm just going to simplify. I'm not going to approximate with our calculator. For instance, there's a copy of 10,000 in there, right? Because 30,000 is 10,000 times 3. And the square root of 10,000 is 100. So we can think of this as 100 root 3, right? Just simplifying square roots. All right, so that takes care of that. That was one unknown. Now we have to figure out theta. So how can we figure out an angle if all we're given is the sides of our right triangle? Well, we have to use inverse functions. All right, that's what an inverse function does. It takes a side, it takes the side, the ratio of the sides, and it gives us an angle. Okay, that's exactly what inverse function does. And again, remember, normally when we take a regular sine function, we take the sine and cosine and tangent of an angle. So the inverse is the opposite. It takes the ratio of the sides equal to the angle. Anywho, so here's our theta. What's sine? All right, sine is SOHCAHTOA, so is opposite over hypotenuse. So the ratio is 100 over 200. All right, so sine inverse of 1/2 is theta. All right, and then just moving backwards, this is just saying sine of what angle is equal to 1/2. Do you guys remember? It's one of our special angles. Sine of 30 degrees, sine of pi over 6 is equal to 1/2. Sine of pi over 6 is equal to 1/2. So what's the angle? The angle is pi over 6. And you can use 30 degrees too. Sometimes in word problems, we don't do radians as much. Sometimes in real life applications, we do use degrees. So that's an option. Okay, so we are on this last part of the equation. Once we take the chain rule or use chain rule to find the derivative with respect to t of both sides, then we make all our substitutions to figure out d theta dt. And we use the fact that z was equal to 200, and we were able to figure out x, and we were able to figure out theta. So let's make all those substitutions now. Okay, so we have then secant squared of pi over 6 times d theta dt is equal to, let's see, 100 times negative 1 is negative 100. And then x to the negative 2, remember negative puts it in the denominator. Okay, so, and x is 100 root 3. So 100 root 3 squared. So again, that move right there. I'm just saying that this is negative 100 over x squared. Just a little simplifying. All right, and then times dx dt, and dx dt is 8. All right, and again, dx dt, that was original information. All right, so let's start simplifying. So secant squared of pi over 6, remember that's secant is 1 over cosine. So what's the cosine of pi over 6? It's root 3 over 2. And then since it's cosine squared, we're going to square that. Okay, so times d theta dt is equal to, all right, negative 100 over this squared. So we're actually just going to go right back to, here it is right here. It's just going to get us back to 30 grand. All right, so it's going to be 10,000 times 3. That's what that squared is. Okay, so negative 100 times 8, so negative 800 over 30 grand. We're almost done. Big problem, right? So here we just have a final step, well, you know, kind of 2 steps, but we're solving for d theta dt. So we can multiply both sides by root 3 squared to clear that denominator. What is root 3 squared? Let's see. We can distribute the square. Root 3 squared is 3, and then 2 squared is 4. So we can multiply both sides by 3/4 to clear that denominator. Almost at our final answer. D theta dt then is equal to negative, because our angle is decreasing, that's why it's negative. And let's see, we can do some canceling. That'll be 200. This will be 10,000. So 200 over 10,000. So you can just call that this. You can put it in your calculator. And then what are the units? All right, well, let's go to d theta dt. Let's go back to radians. Let's go back to radians, because in calculus we use radians, even in the real life stuff. But temporarily we could have thought of it as 30 degrees. And then the rate of time, we can go back to our original rate, and it was in terms of seconds. So we're going to be looking at radians per second. And then that's your final answer. That's how fast our angle is decreasing when our string is 200 feet out. All right. So let's do one more problem together. I think I have one more problem. And this one's, again, it uses a different technique, which is what we're doing here. We're gathering different techniques to use on a variety of related rate problems. So here we go. We have that a spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks from the spotlight towards the building at a speed of 1.6 meters per second, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? Okay, so lots of rates here, right? We have his speed, 1.6 meters per second, and then how fast is the shadow decreasing? That's another rate. So we are doing related rates again. All right, and what number is this? 18. So related rates, let's draw a picture. So we have a ground and we have a wall and we have a spotlight. And the spotlight is shining, right? Okay, so we have a man or a person and they're walking away from the light and they're walking towards the wall. And we want information about the shadow. Okay, well, the shadow is going to be, light explodes all around. And then when the light hits the man, it's going to stop right here, right? That's what creates a shadow. And then everything else is going to continue. And so the shadow is going to be that distance right there. And it's a vertical distance, let's call it y. Okay, and then notice as our man is going this way. So it starts at the spotlight and then he's going this way. So we'll call that x. As we move towards the wall, right, his height's going to remain the same, but then more light is going to be able to get through. So as he gets closer to the wall, his shadow is going to shrink. So as he gets closer to the wall, his shadow is going to shrink, because as he moves away from the light, like right here, if he was right here, for instance, more light would be able to shine through and his shadow would be smaller. Okay? All right, but I'm going to erase that part. Okay, so what are some things we know? We know the height of this person is 2 meters. We know that the spotlight is 12 meters away. And we know that the person is walking towards the wall at a rate, I'm going to say dx dt. It's the change in distance, is 1.6 meters per second. Okay, so there's our scenario. What do we want to find out? We want to find how fast the shadow is decreasing. So dy dt, the rate of change of this distance, y. When, what? I forgot. How fast is the length of his shadow decreasing when he is 4 meters from the building? Excellent. Okay, well, if he's 4 meters from the building, I'll just write this lightly. If he's 4 meters from the building, that means the rest is x, right? Because x is the distance from the spotlight. So the whole distance is 12. So x is going to be 12 minus 4. So we're going to be looking when x is equal to 8. Okay. So how are we going to solve this? Well, if we look at this picture, we have 2 triangles, right? We have this first triangle, and then we have this second triangle. And what's special about these 2 triangles? They're similar. So let's consider this triangle. And they're similar because all the angles are the same, right? They share all the same angles. And then we'll consider the bigger triangle. And what do we know about these 2? Okay, well, first of all, they share the angles. So just something to note. We don't really need to know the angles. And then we know that this triangle, wherever it moves, the height is going to stay the same because that's the height of the person. So it's going to stay steady at 2 meters. And we know this distance is always going to be x. All right, and x is a function of time. And then over in our bigger triangle, our yellow triangle, y is going to vary. As the man walks closer to the wall, the shadow is going to decrease. So y is a function of time. And then the base of that triangle is going to stay constant at 12. Okay? So we have the situation, we have all the variables, we have rates of change, and now it's time to relate x and y to each other. And they're going to be related to each other using similar triangles. Okay, and let's see, we want to find dy dt. So there's so many different ways we can set up similar triangle ratios, but I'm going to start with y on top. And we have an option. We can go y over 12 and look and say that ratio is equal to 2 over x, or we can do y over 2 equal to 12 over x. It doesn't matter. What am I going to do? Why don't I do y over 12, I'll just stay within the triangle, equal to 2 over x. And we can leave it like this. We can also do a nice cross multiply and get xy is equal to 24. So there's our equation relating our two variables. So what do we do after? We take the derivative, because remember, we're trying to find a rate of change. So we're going to take the derivative of both sides with respect to t. Okay, remember x and y are both functions of time. And this is a product. So how do we take the derivative of a product? We use our product rule. So first function times the derivative of the second function plus second function times the derivative of the first. And now what's the derivative of a constant? It's 0. Okay? All right. So we know, what do we know? We know dx dt. That's a constant. That's given to us in the problem as 1.6. And we want to find dy dt. So again, sometimes it's nice to highlight. Okay, so dx dt we know. So we have to figure out x and we have to figure out y. So how are we going to do that? Well, what do we know? We know we want to find this when x is equal to 8. So that's going to tell us to plug in x is equal to 8. All right, so because that's when we want to find the derivative of y with respect to t when x is equal to 8. So there's that. We don't know y yet. We know dx dt is 1.6 because that's given. So now we have to figure out what y is. And finding y, let's go back to our equation, how we're relating everything together. We want to find y. X times y is 24, and x is 8. So 8 times what is 24? Y has to be equal to 3. Okay, so there's our equation, and we're almost done. So let's solve for dy dt. So we can subtract 3 times 1.6 from both sides, and then divide by 8. Throw that in the calculator. And, oops, I missed our minus sign. We're going to get negative, because remember, dy dt, our shadow is decreasing as we get closer to the wall. Negative 0.6. And now think of the units. We're looking at meters per second. All right. And then that's our last problem we're doing today. And again, these examples are tools in your toolbox, right? They're different ways that you guys can solve other related rates problems, and kind of just going through that thought process, writing your picture, writing out your variables, rates in terms of derivatives, and then trying to figure out how your variables are related to each other. So you can write an equation, take the derivative of both sides, and then use your substitution to figure out your solution.